Yeah, good afternoon. Is it audible?
Good afternoon, sir. Yes, you're audible.
Okay. Okay. In the last class, as we discussed about the differences between the addition polymerization and condensation polymerization, just a brief discussion. Okay. The example for the addition polymerization is we have discussed the thermoplastic resin. Okay. For condensation or step polymerization, we have discussed that thermosetting resins are prepared by condensation polymerization, thermoplastic. Okay. Resins are prepared by addition polymerization. What actually the plastics are, we need to discuss. Okay, this is what we have discussed. Okay, monomers must have at least one multiple bond. Is nothing but addition. Example we have taken ethylene. Okay, it contains a double bond. Okay, ethylene is C triple bond, CH triple bond, CH is called. It is the at least one multiple bonds. Multiple bonds contain single one, more than one bond is nothing but multiple bonds. Here it has two identical or different functional groups. Like nylon 6 is already you have explained the example. Okay, here there we are taking the example of nylon 66. Okay, adipic acid. Okay, CH2 taken 4 times by okay to this. Okay, we are adding carboxylic groups, two COOH groups. COOH and here down COOH, it reacts with hexamethylene diamine. Okay, hexamethylene CH2 taken 6 times diamine NH2 NH2. Hexamethylene diamine reacts with adipic acid. It gives what? Okay, nylon 66. Okay, by the elimination of water molecule, 2 moles of H2O will take in place. The product we found got is nylon 66. The same thing, the monomer must have at least two identical functional groups. See, it has the monomer. This is the monomer and this is one more monomer. These two monomers are combined to form the nylon 66. Okay, monomer must have two identical functional groups. Okay, COOH, COOH, NH2, NH2. These are nothing but identical functional groups. Here, monomers add on to give polymer and no other byproducts are formed. Okay, the monomer itself form the byproduct. Polyethylene gives yes, ethylene gives a polyethylene. Ethylene gives a polyethylene, and here it contains to give the polymer. Byproducts are formed. Here, byproduct is H2O. In the preparation of nylon 66, the byproduct is H2O. Here, there are no byproducts are formed. Number of monomeric units decreases as the number of chain increases. Okay, steadily the number of monomeric units decreases steadily throughout the reaction, but monomers disappear at the early stage of reaction. Okay, whatever we are taking the monomer adipic acid and this what is this hexamethylene okay diamine, hexamethylene diamine, it is not appear in the product, in the polymer, the different polymer, different product we got. We are taking the monomers as adipic acid and hexamethylene diamine, but we got the product is nylon 66. Okay, monomers disappear at the early stage. Okay, it is disappearing at the early stages of the reaction, but here in the addition polymerization it is not taking place. Okay, and these already have discussed. Molecular weight of polymer is integral multiples of monomer. How many monomers will take that much? What is this? Yeah, molecular weight. Higher the polymer formed at the once, here molecular weight of the polymer rises steadily throughout the reaction. It increases slowly throughout the reaction. Thermoplastic resins. Okay, thermoplastics are produced by addition polymerization. Okay, this is important. Okay, thermoplastics are produced by addition polymerization. Example, polyethylene and PVC, polyvinyl chloride, etc. Thermosetting plastics. Thermosetting plastics are produced by condensation polymerization. Example, bakelite, urea formaldehyde. Okay, this we need to discuss in the plastics. Homochain polymers are obtained in the addition polymerization. Heterochain polymers are obtained in the condensation of step polymerization. Coming to the plastics. Okay, what introduction to the plastics, and we need to discuss classification of plastics. Okay, plastics are classified into two types. One is thermoplastic resins, okay, and thermosetting resins. Okay, plastics and resins are synonymous, okay, both are same. Okay, here plastics, introduction to the plastics, classification of plastics. In the classification we have thermoplastic resins and thermosetting resins. Coming to the plastics, what actually the plastics are? Okay, here coming to the plastics, these are also polymers, right? Plastics are polymers characterized by property of plasticity. Okay, here it has a property of plasticity and molded to the desired form. Okay, we can mold the plastic into the whatever the form we need. That is nothing but molded to the desired form when subjected to heat and pressure in the presence of catalyst. When we are going to mold this plastic, when it is subjected to heat and pressure in the presence of catalyst, is called plastic. Okay, the term plastic and resin, okay, don't confuse, both are synonymous, means both are same. Okay, here synonymous, resin is the product of polymerization. Okay, resin is the product, whatever the product we got from polymerization, that we call it as resin. Okay, the term plastic and resins are considered to be synonymous. Okay, both are similar. The meaning of the plastic and resins are same. Okay, here the resin is the product of polymerization. Polymerization, whatever the on polymerization we got the product, no, that we call it as resin. Okay, in the preparation of ethylene, polyethylene. Okay, ethylene is a monomer. Okay, ethylene is a monomer. On polymerization we got polyethylene. Here this polyethylene is called resin. Okay, this polyethylene is the polymer we got from the monomer ethylene. Monomer ethylene. This polyethylene we call it as a resin. Okay, it is a product of polymerization. Product of polymerization is called resin. Okay, here in the example we are taking ethylene monomer on polymerization. On polymerization, you will get the product polyethylene. Okay, polyethylene is a resin called. Okay, the forms, and this forms a major part of the plastic. Okay, resin forms the major part of the plastic is resin itself. Okay, plastics are materials obtained by mixing the resins with other ingredients. Okay, in the compounding of plastics, we'll see what are the ingredients we are using in the preparation of plastics. In the preparation, okay, resins are the major part of the plastic is the resin. Okay, major part of the plastic is the resin. Resins are the materials obtained by mixing the resin with other ingredients like catalyst. Okay, there are different in the resins. The preparation of resins, we have different ingredients we will use. We'll see what are the ingredients required for the plastics in order to mold into a desired shape. Okay, plastics are nothing but polymers characterized by property of plasticity, molded to desired form. Whatever the form you want, you can mold it. These plastics when they are subjected to heat and pressure in the presence of catalyst. In the presence of catalyst. Now, these plastics are resins are considered to be synonymous. Okay, the major part of the plastic is the resin, and the plastics are materials obtained by mixing the resin with other ingredients to impart the special properties. Okay, special properties of plastics are obtained by mixing the resin with other ingredients to impart the special engineering properties to the plastics. Okay, special engineering properties to the plastics. We are going to add some ingredients to the resin. Okay, now coming to the plastics are characterized by characteristics of plastics. Okay, what are the characteristics are present in the plastics? Here this is light in weight. Plastics already, you know, they are lighter in weight, and they have good thermaline electrical. They act as a good thermaline electrical insulator. Insulation is nothing but it does not allow the electric current to pass through them. So we call it as good electrical insulations. Okay, and these plastics are high corrosion resistance. Okay, these plastics never undergo corrosion. Okay, corrosion is nothing but rust formation, but these plastics never undergo any rust formation. So it is a resistance to corrosion. Okay, high corrosion resistance, and it has the easy workability. We can mold easily. Okay, we can mold the plastics very easily, drilling, etc. They are highly chemical inert. They cannot react with other chemicals. So highly chemical inertness, and it require low maintenance cost. It require low maintenance cost, high abrasion resistance. Abrasion is nothing but smoothness to the surfaces. Okay, smoothness that present on the surface of the plastic, high abrasion resistance, and toughness, impermeability to water. They are not permeable to the water. These are the characteristics of plastics. Okay, plastics are characterized by lighting weight, good thermaline, electrical insulators. Okay, they have good electrical insulators. Insulators are nothing but which does not allow the electric current to pass through them, is nothing but insulators. Okay, high corrosion resistance, easy easy we can workability. We can modify the plastics into desired forms as we like we can molding and for drilling, etc. High chemical inertness, low maintenance cost. Okay, it requires a low maintenance cost and high abrasion resistance. Okay, and toughness, impermeability to water. These are the characteristics of plastics. Now coming to the classification. Okay, how we are going to classify the plastics. Yeah, coming to the classification of plastics. Here, plastic resins. Okay, plastics are nothing but resins. Okay, major part of the major part of the plastic is not, we called it as a resin. So plastics or resins are classified into two types now. They are classified into two types. One is thermoplastic resin and thermosetting resin. Thermoplastic resin and thermosetting resin. We need to discuss what actually this thermoplastic resin and what is thermosetting resin. Okay, what actually the thermoplastic resin is, what actually the thermosetting resin. The thermoplastic resins are those which are softened by heating. Okay, these are actually harder. Why this thermoplastic polymer is harder? Because it has, okay, here thermoplastic resin is hard when before heating. Okay, these resins, those are those in which soften by heating and harden on cooling. Okay, before we are passing the heat to the thermoplastic resin, okay, they are harder. Here, whatever the bond that is present between this, in between the monomer chains are covalent bond is present. Covalent bond is present. So due to that, it is on heating, these covalent bonds are broken and forms the no linkage between the monomers will be taken place. These are before heating, before heating the thermoplastic resins are. Okay, those which are softened. Okay, these are we are converting this harder thermoplastic into the before we are passing the heat. These are harder in nature. Okay, because it consists of covalent bond between the monomers. Between this is the monomer. In between the monomer chain, okay, it contains the covalent bond. Okay, this is the weak bond. Okay, these weak bonds on heating, it gets converted into the no links between the, okay, here it becomes softer. Okay, on hardening the thermoplastic. Okay, before heating it was hardening, hard rubber. Okay, hard polymer. On heating it is converted into the softer. The reason is whatever the bond, that is intermolecular forces between the polymer chains or breaks, and here facilitates the easy momentum of the polymer. Okay, whatever the intermolecular forces but that present in between the monomer chains. Okay, between the monomers has been broken down. Okay, this monomer chains has been broken down, and it easily facilitates the momentum of monomer chains. Okay, here it is easily moving takes place. So this hard thermoplastic polymer gets converted into the softened state because there is a the action of heat. What happens on heating? Whatever the intermolecular forces between the monomer chains, polymer chains, in between this, it is the intermolecular forces are present. These forces has been broken down, and it facilitates the easy momentum of the polymer chain, which makes them soften. Okay, we are converting the hard rubber on heating. Okay, hard thermoplastic resin has been converted into the soft. Okay, this is the when again on this soften on heating, it gets converted into the again what hard rubber. See, when on cooling the plastics, on cooling this, whatever we got this, on heating we got the soft rubber. To this again we need to cool the plastics. Okay, on cooling the plastic, the intermolecular forces reappears. Okay, the intermolecular forces present between the polymer chains reappears, holding the polymer chain in the fixed position. Okay, which makes the rubber rigid and hard. Okay, which makes the rubber rigid and hard. Okay, here this is generally prepared by addition polymerization. Okay, already in the differences between the comparison between the addition and condensation polymerization, we have discussed. Okay, thermoplastic resins are prepared by addition polymerization. Okay, addition polymerization, we have prepared the thermoplastic resins. It is very simple, ma. The thermoplastic resins are those which can be softened by heating and hardened on cooling. Okay, on cooling here, on cooling, what we have to do, we need gets converted into the hard thermoplastic resin. Okay, hard resin. It is what resins goes with soften on heating and harden on cooling is called thermoplastic resin. Okay, the reason behind this is due to the action of intermolecular forces between the polymer chain. Okay, whatever the bonds present between these intermolecular forces has been broken down, and it facilitates the easy momentum of the chain, which makes the resin to be softened. Okay, which makes the resin to be softened on cooling. On cooling, whatever the soft rubber we got, on cooling it becomes rigid and hard. Okay, whatever the intermolecular forces reappears, it reappears holding the polymer chains in the fixed position, which makes the rubber to rigid and hard. Example for thermoplastic resins are polyethylene, polyethylene, polyvinyl chloride, polystyrene, and PTFE. The full form of PTFE is polytetrafluoroethylene. Polytetrafluoroethylene or Teflon. Okay, or Teflon are the examples for the PTFE, polytetrafluoroethylene. Polytetrafluoroethylene are the examples for the thermoplastic resins. Just quite opposite of this thermoplastic resin is thermosetting resin. Thermosetting, what actually the thermosetting resins are? Here, thermosetting resins are the resins which during molding process get hardened. Okay, it gets hardened. Later can be softened by heating. Okay, initially it becomes hardened. On molding, what happens? This is the reason for this is it poses a three-dimensional cross-linked network. Okay, here it poses a three-dimensional cross-linked network. Here see the monomers, it has three-dimensional cross-linked network. But in the thermoplastic resin, there is no links between the polymer chains. Helps the momentum. Okay, this helps to the momentum of the polymer. But there is no here. Okay, cross links present in between them. So links between the polymer chains stops the momentum. It stops the momentum okay, three-dimensional network, cross-link network polymer chains made up of covalent bonds. Okay, it is made up of covalent bonds. These strong covalent bonds maintain the strength of the polymer even at the high temperature. Even at high temperature, there is in whatever the bond present between the polymer chains, in between the this chain. Okay, this bond is a strong covalent bond. Okay, strong covalent bond. Here it helps to the maintain the strength of the polymer even under high pressure, high temperatures also this covalent bond never breaks. Okay, that is the reason. Okay, it is hard and cannot. Okay, this is a hard rubber. It never breaks. Okay, whatever the bond present between the polymer chain, that bond is a strong covalent bond is present. Okay, it makes the three-dimensional cross network cross link network polymer chains made up of covalent bonds. So these strong covalent bonds maintain the strength of the polymer even at high temperature. Even at high temperature, there is a no breakage of the strong covalent bonds in between the polymer chain takes place. So these are hardened and cannot be softened on cooling. The reason behind that is because whatever the bond present between these polymer chain are strong covalent bonds. It makes the during the molding process also it is remains strong. Okay, it remains a hardened. Okay, cannot be converted into the soften by heating also. The reason is presence of strong covalent bond between the polymer chains. Okay, the reason is strong covalent bond between the polymer chains. Thermosetting resins possess three-dimensional cross-link network polymer chains made up of covalent bonds. This strong covalent bond maintain the strength of the polymer even at high temperature. If you pass the high temperature also, these bonds never breaks. So that is the reason these are thermosetting resins are hardened. Okay, hardened and cannot convert it into the softened by the heating also. Okay, on heating also we cannot convert this into the soft rubber, but in the thermoplastic resin we can convert the hard into the soft. And again on cooling the soft become the harder. Okay, but here it does not takes place in the thermosetting resin. Okay, these thermosetting resins are prepared by condensation polymerization. Okay, condensation or step polymerization. Condensation polymerization, we can prepare this thermosetting resins. Thermosetting resins are obtained by the condensation polymerization or step polymerization. Step polymerization. Okay, the reason behind why these thermosetting resins are harder means we cannot convert into soft the whatever the bond present between the polymer chain. Okay, this is a polymer chain. In between the polymer chain, the bond that is present is strong covalent bond. Okay, we cannot this is the strong covalent bond. We cannot convert in even at the high temperatures. We cannot break this bond even at the high temperatures. Examples for the thermosetting resins are bakelite and epoxy resins. Okay, the switches bakelite. Okay, whatever the switches made up of this bakelite only. Okay, thermosetting resins examples bakelite and epoxy resins. Okay, bakelite buttons are also made up of bakelite. Here the switches are made up of the polymer bakelite. All these are the examples, and the bakelite buttons are also in the preparation of buttons also it is used. Here coming to the thermoplastics and thermosetting plastics. Thermoplastics are nothing but there. Okay, here whatever the bond present between the polymer chain is weak bond. Okay, weak van der Waals forces are present in between the polymer chains, so it easily break down. It undergoes breakdown when it in the presence of heating. Okay, it breaks to form. It helps to the momentum of the polymer chain. The easy momentum of polymer chain takes place. Okay, again on cooling. Okay, heating. Okay, initially it was hard rubber. On heating, what happens? Whatever the bonds present between these polymer chains has been broken down. Okay, broken down. It leads to the momentum of easy momentum of polymer chain. Okay. Okay, the rubber we got is the softened rubber. On cooling, it gets converted into the hard rubber. Again, the intermolecular forces becomes rigid. Okay, and it becomes hard rubber. But it is not happening in the thermosetting resins. Okay, thermosetting resins are harder even at very high temperature. Okay, we cannot convert this into the soft rubber. The reason is whatever the okay, it is a the bond present is a covalent bond. Okay, strong covalent bond makes the polymer to be hardener. Yeah, coming to the differences between thermoplastic and thermosetting resins. Okay, what are the differences between thermoplastic and thermosetting plastics? Yeah, what here the example for the thermoplastic, okay, addition polymerization is by thermoplastic. Okay, addition is thermoplastic, condensation is thermosetting. On thermo, okay, it is by condensation polymerization. Addition, condensation, polymerization. Now coming to the thermoplastic resins are thermosetting plastics. Okay, what are the differences between thermoplastic and thermosetting plastics? Thermoplastics are usually formed by addition of polymerization. Okay, on addition of polymerization, these thermoplastics are formed. Okay, this thermoplastic setting. Okay, thermosetting plastics are often formed by condensation. Already we know this. It is a long chain linear polymers held together by weak van der Waals forces. Okay, it is the whatever the bond that is present in between the polymer chain is the weak van der Waals forces. Okay, weak van der Waals held together. The long chain polymer linear polymers are held together by weak van der Waals forces. Okay, that is the reason whatever the bond present between these chains are easily broken down and it gets converted into the soft rubber. On cooling, we can get again it reappears like the hard rubber. But here it is not happening in the thermosetting plastic. The reason is whatever the intermolecular forces that present between the polymer chains is the strong covalent bonds. This covalent bonds, okay, makes the strength of the rubber plastic. Here it contains a three-dimensional network. Okay, here thermosetting plastics are contain three-dimensional network structure constructed with strong covalent bonds. Strong covalent bonds. Here usually becomes soft on heating. On heating, hard rubber becomes soft, and on cooling, it becomes again okay, hardened, stiffen on cooling. Means it become harder on cooling, but it does not become soft on heating. Okay, it never undergoes okay, soft on heating. It is expensive. Thermoplastics are expensive and it is cheaper. These thermosetting plastics are cheaper. Here thermoplastics is soluble in organic solvents. Okay, these are soluble, easily soluble in organic solvents. Soluble in organic solvents. Here thermosetting plastics are insoluble. They are not soluble in organic solvents. They are not soluble in organic solvents. They are usually soft. Okay, usually soft, weak and less brittle in nature. Okay, these thermoplastics are soft, weak and less brittle in nature, whereas these are hard. These are hard, strong and more brittle in nature. Hard, strong and more brittle in nature. Here we can remold this thermoplastic resins. We can remold this thermoplastic resin. We cannot remold it. They cannot be remolded. Example for the thermoplastic resin is polythene. Polythene, and the example for the thermosetting plastic is bakelite. Okay, example, we are taking polythene for the thermoplastic resin, and thermosetting resin is bakelite. Okay, this is the differences between thermoplastic and thermosetting resins. Thermoplastics are usually formed by addition polymerization. It is by condensation polymerization. It contains long chain linear polymers which are held together by weak van der Waals forces. Here it has strong covalent bonds. Yeah. Here it is a long chain linear polymer held together by weak van der Waals forces, but it contains three-dimensional network. Okay, three-dimensional network structure constructed with strong covalent bonds. It becomes soften on heating and stiffen on cooling. Sorry. Okay. Okay, harder on cooling, but it does not become soft on heating. On heating, it does not become soft. These are expensive, they are cheaper. Thermoplastics is soluble in organic solvents. Thermosetting plastics are insoluble in organic solvents. They are usually soft, weak, and little brittle in nature. They are harder, strong, and more brittle in nature. They are remolded. We can remold the thermoplastic resins, but we cannot remold the thermosetting plastics. Example for the thermoplastic is polythene, and here it is bakelite. This is about differences between thermoplastic and thermosetting resin. Classification of plastics. Plastic is nothing but the polymer. Okay, and it has characterized by property of plasticity, molded to desired form. We can whatever the form we want to, we can mold the plastics when subjected to heat in the presence of catalyst. Heat and pressure in the presence of catalyst, we can mold this plastic into the desired shape, desired form. Okay, and this the resin is the product of polymerization, polythene. Okay, what are the compounding of plastics? What is compounding of plastics? Okay, whatever the ingredients we are used to prepare the compounding in the compounding of plastics. See, there are several polymers like polymethyl methacrylate, polystyrene, etc. can be molded without application of additives. Additives, but many of the plastics like phenolic and amino resins and cellulose resins, etc. require additives for their molding into the proper forms, proper shapes. Some polymers like polymethyl methacrylate, polymethyl methacrylate and polystyrene. These polymers does not require any additives, but many of the plastics like phenolic amino resins and cellulose resins, etc. require additives for the molding into proper forms. This requirement of adding of chemical admixes, nothing but additives to the plastics, is nothing but compounding of plastics. Compounding of plastics is nothing but compounding of plastics is a process of adding chemical admixes, is nothing but additives. Okay, adding chemical admixes which increase the physical properties of the molded products, which increases the physical properties of the molded products is called compounding of plastics. Compounding of plastics. Here, the following are the important additives. Additives are nothing but chemical admixes here. The process of adding chemical additives which increase the physical properties of molded products is called compounding of plastics. Okay, here the following are the important additives added to the polymer resin. Okay, these are the important additives, chemical admixtures. Okay, these are going to add to get the desired form of the plastic. First one is resin. Okay, major part of the plastic is resin. Okay, first one is resin. Second one is plasticizers, resin, plasticizers. Okay, next fillers, stabilizers, lubricants are nothing but oils. Okay, accelerators are catalysts and coloring materials. Okay, in order to get the plastic in a desired form, we need to add this chemical additives. We need to add this chemical additives to the plastic. The important additives added to polymer resin is resin, first one, plasticizers, fillers, stabilizers, lubricants, catalysts or accelerators, and coloring material. The last one is coloring material. In order to make the proper desired form of the plastic, we need to add all this. Okay, we need to add all these additives to get the polymer resin. What actually the resin is? Okay, what is a resin? Okay, this is the resin is nothing but binder or polymer material which constitutes the, already I have said, major portion of the plastic is the resin. Okay, major portion of the plastic forms the resin. Okay, it is a binder or polymer material which constitutes the major portion of the plastic. As described earlier, okay, there are two kinds of resins. One is, okay, one form of resin is fusible and remolded, known as thermoplastic. Okay, but whereas other is cross-link non-fusible, thermosetting. Okay, we cannot convert the this resin into desired form. They are not cross-link non-fusible form of resin is known as thermosetting plastics. Okay, resins are of again two types. One is thermoplastic, thermosetting. We have discussed what is thermoplastic. Thermoplastic on heating, it forms. Okay, initially it was harder. Okay, whatever the polymer chains that made up of these thermoplastics are weak van der Waals forces. The bond present between the polymer chain has been broken down, so it gets converted into the soft thermoplastic softener. On cooling this softener, again we convert it into the hardener. Okay, hard on cooling. Okay, this is nothing but one form of resin in which fusible line we can remold it. We are converting hard into the soft. Soft again we are converting into the hard. This is called as remoldable. Is known as thermoplastic. Okay, the kinds one form of resin is the fusible and remoldable. Okay, this is remoldable is nothing but thermoplastic, and whereas cross-linked, okay, three-dimensional cross-linked non-fusible form of resin is known as thermosetting plastics, which required catalyst. Okay, for this it requires catalyst during the molding process. Here, polyethylene resin. Polyethylene example we have taken. Okay, polyethylene resin and PVC, polyvinyl chloride. Polyvinyl chloride are the two types of resins. Okay, it is forms a major portion. What actually the resin is a major portion of the plastic. Okay, it helps in the binder of the polymer material and which forms the major portion of the plastic. And these resins are again two types. One is thermoplastic resin and thermosetting resin. Thermoplastic is nothing but one form of resin, fusible and we can remold it, is known as thermoplastic, and which is non-fusible cross-linked form of resin is known as thermosetting plastic, which is requires catalyst during the molding process. Requires catalyst during the molding process. Now coming to the plasticizers. What actually these plasticizers are? Okay, the plasticizers are nothing but chemicals. Okay, here these are the chemicals added to the resin. Okay, major portion of the plastic is resin, right? You're adding the plasticizers to the resin. Okay, chemicals that are nothing but added to the resin to increase their plasticity, and flexibility. These plasticizers are the chemicals that are added to the resin to increase their plasticity and flexibility. Okay, these plasticizers molecules get inside the polymer chain. Okay, these plasticizers moves inside the polymer chain and neutralize the intermolecular force of attractions between the micromolecular polymer chains. The aim of this plasticizer is it get inside the polymer chain. Okay, it moves inside the plasticizers moves inside the polymer chain and neutralize the intermolecular forces but present between the polymer chains. Okay, and the intermolecular force of attraction between the micromolecular polymer chains. Okay, here the breaking of intermolecular forces between polymer chains facilitate the greater freedom of the momentum. Okay, if this plasticizer moves inside the polymer chain, okay, it helps to break the bonds present between the polymer chain, so greater freedom of momentum of the polymer chain, thereby increasing the flexibility of the plastics. Okay, it makes the breakage, the plasticizer helps to breakage of the bonds, intermolecular bonds present, bonds present between the uh, polymer chains. Okay, and it helps to increase the flexibility of the plastic. It helps to increase the flexibility of the plastics. On increasing the flexibility of the plastic by the addition of plasticizers reduces the strength and chemical resistance of plastics. On increasing this plastic flexibility by addition of this plasticizers, what happens means it reduces the strength and chemical resistance of the plastic. Okay, the most commonly used plasticizers are vegetable oils. Okay, the vegetable oils, triglycerol phosphate, tributyl phosphate, triphenyl phosphate, etc. Okay, these are the commonly used plasticizers. Okay, commonly used plasticizers are vegetable oils. Okay, what it makes means it increase the, these are the chemicals that are added to resin to increase the plasticity and flexibility of the plastics. Plasticity and flexibility of the plastics. It helps to break the intermolecular forces between the polymer chains and facilitates the greater freedom of momentum of this polymer chain, thereby increase the flexibility of the plastic. Okay, whatever the intermolecular forces that is present between the polymer chains has been broken. Okay, is been breaking by these plasticizers and makes them flexibility of the plastics. Okay, thereby increasing the flexibility of the plastics. As the flexibility increases, what happens means it reduces the strength and chemical resistance of the plastics. Okay, commonly used these plasticizers are vegetable oils, triglycerol phosphate, tributyl phosphate, triphenyl phosphate. These are the examples, etc. Okay, these are acts as a plasticizers to increase the plasticity of the and flexibility of the resins. Increase the plasticity and flexibility of the resins. The use of plastics. Okay, see the structure of triglycerol phosphate. Okay, triglycerol phosphate structure is this one. Okay, triglycerol plasticizer. It acts as a plasticizer. Vegetable oil, triglycerol phosphate, triphenyl phosphate, tributyl phosphate, triphenyl phosphate. All these are the plasticizers. See in the polymer chain, this acts as a plasticizer. Here, this is a polymer chain. This is a plasticizer. Okay, it helps to the increase the plasticity and flexibility of the plastics. Okay, plasticizer acts as a to increase the plasticity and flexibility of the plastic. Examples we are taking which acts as a plasticizers are vegetable oil, tricyl phosphate, tributyl phosphate, triphenyl phosphate. Okay, these are the examples which helps to acts as a plasticizer, which increase the flexibility and plasticity. Okay, flexibility and plasticity of the plastics. Next, fillers. Okay, this we'll discuss in the next class, ma. Fillers, lubricants are nothing but oils, and catalyst, accelerators are catalyst. Okay, these are added to thermosetting plastics in order to accelerate. Means catalyst in the polymerization of fusible resin to cross-linked form. We are adding to this thermosetting plastic, thermoplastics and thermosetting plastics. Okay, this is accelerators are mainly used for the thermosetting plastics because they, if you, they are not converted into any form of the okay on heating us because the presence of strong covalent bond between the polymer chains. We are adding this accelerator to the thermosetting plastics in order to accelerate polymerize the fusible resin into cross-linked form during the molding operation. Okay, these are compounding. These are the different. Okay, ma. If you have any doubts, you can ask. It's time up. If you have any doubts, you can. Stop sharing the screen. If you have any doubts, you can. Okay, thank you one and all. Thank you.